Hi, this video is going to be a doozy. This is a big video. There's a lot of meaty content in this. This is not for the faint of heart. All right, in this video, we are going to be looking at the distribution of autoregressive parameters in statistical models for time series. And what we want to do, we want to consider the large sample aspect. That way, the reason why we're doing large samples is that we'll have enough data to get a good, solid representation of our coefficients. Now, a lot of people have heard about the central limit theorem. Basically, if I have enough data, I know what the distribution of something I'm trying to estimate. Now here, we're going to be trying to estimate the coefficients in an autoregressive time series model. And what we're going to do is we're going to theoretically pencil and paper work through the details of this so that we have a very full and complete understanding of the autoregressive parameters that we estimate, the estimated values. Now, this video is intended for those who are pretty deep into statistics. And so just giving you fair warnings on that. This is a pretty meaty proof, a lot of steps to it. It's good stuff, but we're going to be taking a big bite of the apple if you're going to be watching this video. All right, so we're going to be talking about the large sample distribution of autoregressive conditional least squares estimators. All right, so we're going to be looking at the estimation of the autoregressive coefficients, and we're using large sample to be able to use convergence theorems. Now, all this is coming from Appendix B of Time Series Analysis and its Applications. Here are the authors of the textbook. Here's our GitHub page. And this textbook can be downloaded for free through UCF's library. All right. Here is what we want to prove using proofs in mathematics. All right, so here is the theorem for large sample distribution of autoregressive conditional least squares estimators. So when I say autoregressive conditional least squares estimators, this is the one way of estimating the parameters in an autoregressive model. All right, so let's go ahead and say that this is the autoregressive process, the theoretical time series that we want to understand. And this is where our data is coming from. We see output of this process in real life. And what I want to do, I want to model this using an autoregressive model. Now, we're going to go ahead for the moment and say that we know what the parameters are, the degree of the autoregressive model. And we just need to estimate what are the coefficients. And what we're going to do, we're going to use the least squares method of estimating that. Why are we going to do that? Because the math is very clean, very easy. We can fully, completely understand from a theory point of view what's going on with those estimators. Now, to make our life just a little bit easier while we work through the proof, we're going to say that we have mean zero and IID white noise. And, let's go ahead and just think of it as independent, identically distributed Gaussian white noise is definitely a reasonable thing to, in your mind, think of. The result is a little bit more general, but as you work through, think about it that way. Now, what we're going to do is we're going to make the assumption that on our white noise, the fourth moment has a finite expected value. That's really what we want here. We need a finite expected value on the fourth moment. It's not a really steep requirement. Basically, why do we need that? We need that so that our variance and covariance estimates have the central limit theorem and other theorems kicking in to help us work through this proof. Okay, so we're going to go ahead and say that the estimated coefficients of our fitted model is asymptotically normally distributed. So this is a vector. So we have multiple parameters that we're estimating. There's going to be a lot of vectors going on in this proof. This is a vector of the coefficients, and we're going to say that it's asymptotically normal to an expected value of, well, what we're trying to what we're trying to estimate. So here, this phi represents the true correct parameters of this autoregressive time series process. And then we're going to say that we have this variance here. And so this is a multi-dimensional normal distribution. And so here is the variance coming from our white noise. You notice that sample size is shrinking things down. And here, this is the covariance matrix that we get from it's the covariance between observations on our our time series process. Now, also, in addition, we're going to say that the estimated variance of our white noise process will converge to the correct variance of our white noise process. Okay, and how we're going to get this going, this auto covariance term, is that we're going to just take vectors of our time series process, and I'm going to do the vector as a column. I'm going to take the vector as a row vector, and we're going to multiply. And when in this situation, we're talking about stationary time series. So we have an expected value of 0. So this is an empirical covariance term in this. And you'll notice that we're averaging it up. So this here is the empirical covariance matrix, and it will converge to the correct covariance matrix. And we see that the inverse will be appearing in the variance, the multivariate normal variance of our estimated parameters. All right, there's a lot here. If you're not familiar with time series, think of this as what is the distributions of the coefficients in regression. All right, think of this as, this is similar to the idea of, here are my estimated coefficients in regression. Here are the true coefficients, and here is the variance on the estimator. Okay, so there is a lot of stuff to work through here. So we're going to take a small bite of the proof, then we're going to take a big bite of the proof, then we're going to take a small bit. So the last thing we will do is work on this variance convergence and probability. All right, so the first bit, recall that the expected value of this vector multiplication, which will be, actually, something I need to back up on. The author of the textbook is using this t-1 subscript to represent all of the backshift values of our time series. All right, so here, this is, think of this one, this is the current time series value at time t, and this is all of the previous time series values before that. So this is a vector of values, this t-1. Every time you see t-1 in the subscript, that is a vector of values in the past, all the backshift previous values. But when you see x of t, it's the current value that we're interested in. And so there is a doubling up of notation in this proof, but the authors chose to do this way so that we don't get, the notation doesn't get unwieldy. It doesn't get to be too much. So, just be mindful of that as you work through. I chose to do it the way the authors did to be consistent if you look at the textbook. All right, so here, when I do that column vector by row vector multiplication, I'm going to get a a matrix, a square matrix, and the expected value of each entry is going to be the covariance for the time series process that I'm interested in. All right, so that's the expected value. All right, so because we have a finite fourth moment, what this says, the reason why this is important is because this says, hey, I can use a central limit theorem on this, even though it's the product of observations. All right, well, because of this fourth moment, I can use central limit theorem. I can go ahead and it's pretty much going to work out the way I want to for this part of the proof right there. All right, so x sub t minus 1, this is a vector of 1 to p backshift observations. And so here, when you look, whenever you see x sub t minus 1, this is what is being represented. So we have a degree p time series process that we're trying to model, and we're going p backshift, p back in time on our observations. And then here, because of that finite fourth moment, this is going to converge on its expected value. All right, so here, the reason for that is because I'm in fact invoking an average. Therefore, we're going to have convergence in probability to its expected value. This line should actually be moved down to here, but all right. And so we have this result. All right, that is the easiest step in the entire proof. So let's go ahead and proceed. Now we're going to start thinking about the distribution of our estimated coefficients. All right, what we're going to do, we're going to use the basic approximation theorem, and this is going to be doing the heavy lifting. There's a lot of things going on. All right, so the basic approximation theorem. One, I have a process I'm interested in. Then I'm going to take a double indexed observed value statistics, double index statistics that are close to each other in terms of convergence in a particular manner. And if those are close and that double indexed statistic is close to a single indexed statistic in convergence, when I keep one of the indexes constant, if I keep one of the indices constant and let the other one run to infinity, if that converges to another statistic, and I understand the convergence of this when I let the index go to infinity, convergence and distribution, what is going to end up happening is that the original value that I'm interested in will converge to what's over here. So what's going on? We have what we're interested in. That's one. Two, we're going to have a double index statistic that will approximate the first one, the one that we're actually interested in. Now, this double indexed, we're going to let one of the indices go to infinity. We'll let the other one be constant. All right, that gives me the third one. If there's convergence from here to there, then I've got something else going on here. So we're going to take the point of view that we understand this completely. Now, after I'm done letting one index go to infinity, I'm going to let the other one go to infinity. And this will be a distribution. So under some criteria of what's going on, what's going to end up happening is that the one that we're interested in, which can be approximated by double index, which can be approximated by single index statistic, which converges to a distribution, then the one that we're interested in will be asymptotically close to that last convergence. There's a lot of steps. There's a lot of bridges in that. All right, so there's 3 bridges that we have to get through this proof. All right, so let's go through this. All right, so our autoregressive degree P process is this. All right, so that is just standard autoregressive time series. Our least squares estimate it's just going to be that the empirical covariance matrix inverse times the vector of empirical covariances. Okay, so now I'm going to do multiplication. And so here we do the multiplication. We're going to put things into position. Now, you'll notice here that this formula goes from p plus 1 up to n. So one of the tricks that we're going to do in this is that instead of working with this p plus 1 to make the proof easier to work through pencil and paper, to save my wrist some work, to make it a little bit easier just to slug through this, instead of going from p plus 1 to n, we're going to start at 1. All right, so notice that here I've got 1, here I've got 1. This is the same as that, except where we start the summations from. Okay, so why are we doing that? It's just going to be easier to work through the proof. Now, why is this reasonable? Well, if I'm talking about looking asymptotically, I'm talking about convergence, I'm talking about looking at the large sample aspect of it. When I get a crap ton of data, when I get tons and tons of data observations, it's not going to really be that big of a difference to go from here to here or vice versa. So what I'm going to do, I'm going to do the proof for this, but then we're going to go, hey, I'm going to actually, in fact, get the same convergence result either way. So in the proof, I'm going to go with the version that is easiest to work with and go that asymptotically in the limit, they're close to each other. So it's going to be perfect. It's going to be beautiful. All right. So now let's keep going with this. All right. So what we've done here is that I'm just going to work with this estimator instead because it's easier from a pencil and paper mathematical proof version. And what I'm going to do, I'm just going to go through, I'm going to start working through some stuff. All right, so I'm going to take my estimator. Now, you'll notice I replace this x sub t with what do I have from the autoregressive process. Okay, that's easy peasy lemon squeezy. Now what I'm going to do is I'm going to work through and I'm going to rewrite everything in a manner that's easier to digest. Or I realize that if I look at this phi as a vector and I look at the x, if I look at this as a backshifted vector, I can in fact represent this summation as a dot product or matrix multiplication. And so I'm going to replace this with this as matrix multiplication just to make things a little bit smaller and more compact. So I have to write less and I have to interpret less as I work through this proof. All right, so now what I'm going to do, this is just a scalar and this is just a scalar. I'm going to go ahead and take this vector and I can distribute like this. Okay, like this. Now you'll notice that I've got vector, vector, and vector. All right, so now what are we going to do? Well, I look at this and I've got a kind of a decent sized summation here. I'm going to take this part and I'm just going to distribute because I'm allowed to do that in matrix multiplication. All right, so I'm going to distribute this inverse part here across. All right, easy peasy lemon squeezy. So I've got two terms inside the summation. You could distribute just like you do in a matrix algebra class. All right, so now I've broken up things into two parts. Now I'm going to look here. I notice that I've got an inverse matching up with exactly the same thing. So they're going to cancel each other out. So if I multiply this part, in fact, I have the identity matrix. Well, the identity matrix does nothing in matrix multiplication. So I know that here, this whole part is just going to be phi. And so boom, I'm just left with this. All right. And so that's cleaned up nicely. and I'm left with the remaining part. All right, so now let's go ahead and subtract both sides, the actual fee. So this is the actual value that we're trying to estimate. And so now on my left-hand side, I have my estimator minus the true value. Well, it looks a lot like an error, right? And remember that this is the difference between two vectors. Two vectors are getting subtracted. And so I have a formula. Now what I'm going to do is that for things that we're going to be doing later on for that distribution aspect, I'm going to go ahead and multiply both sides by n to the power of 1/2, the square root of n. Now, notice I've got 1 over n on the inside of an inverse. All right, so because it's on the inside of the inverse, if I was to try to pull this out in front, that would in fact be an n. And so here, this is the same. If I put out front, outside that parenthesis with the inverse up here, this 1 over n would be in fact just an n divided by the square root of n. I'd be left with the square root of n. So I have a balanced equation. All right, so now let's take a look at this part here. That is a vector of past observations. All the observations we have up until the last P observations when we look at when we're looking for the next thing to pop. We're anticipating the next value. And this is the last P observations I have. Well, here, this is from the past, and this is going to be the value, the random variable that's going to be involved in my next observation. Well, part of the stationary time series aspect that we're working with, we're making the assumption that my white noise is independent of all previous observations. So I know that the expected value on here is going to be equal to 0. Boom. Because here, when I take this expected value, we assume that this is independent of all past values. This is all past values. So by independence, we can factor the expected value. And here, I know the expected value is equal to 0. Boom. All right. Now, let's keep on going. Well, one thing that I can do to keep going with this is I can take the covariance aspect on this term also. All right, well, what is going to be the expected value on that? So I take this, and this will be a matrix. So this is a row vector. So this is a row vector. This is a number, a scalar. Sorry, I said row vector. That's incorrect. This is a column vector. This is a column vector. This makes this into a row vector. When I multiply, this is going to be a square matrix inside here. I'm going to take the expected value of the square matrix, okay, and, well, what's going to end up happening is that what I'm going to get here, that's just regular old numbers, I can factor that out. Once again, we have independence, so I can go after I get it factored into a different position. All right, so I have vector, so I'm doing matrix multiplication, but in your matrix multiplication, regular old numbers, scalars, can move front, back, in the middle, wherever it's convenient for us. And we're going to do that. We're going to take these two and move them to the right-hand side of the multiplication. And you can see that's where it lands over here. After I move it over to the right-hand side, because of the independence aspect we just talked about, I can factor the expected value. All right, so now when I take this, the expected value here, I'm going to get gamma. And when I take the expected value here, I'm going to get the variance of our white noise process. Boom. All right, things are looking good. Now, if I think about this for a moment, another way that I can look at this, and it's completely reasonable, completely okay for us to do this, if I only consider larger values of h, and I look at the expected value here. So if I take this, with this, so I'm doing a covariance computation. You notice that here we have matching, so we get potentially have matching subscripts because we don't know what H is. But if H is large enough and positive, or large enough and negative, basically far enough away from the other values, the other subscripts, what we can do is we'll know that this term will be independent of all the other observations. So if I have a large enough H or a small enough H, negative and large in magnitude, this will not have any, this T is not going to match up with any of the subscripts in here and none of the subscripts in here, no matter what. And so I can factor out this part of it. And so in fact, I can get an expected value of 0. So that tells me for large enough out, if I shift far enough forward or shift far enough back, the current white noise term will be independent of those values. All right. All right, so now let's consider the mean squared convergence approximation of x of t. All right, so here, what we're going to do is that we're going to take an approximation using previous white noise terms, which is okay as long as we have a causal process. And here are the coefficients. All right, so what we're going to do is I'm going to say that u sub t exponent m is the vector that I get when I take the m data points approximation of x of t minus 1, the m data points approximation of t minus 2 in time, and so on all the way down, multiplied by that white noise term. All right, so now once I do that, so you can see what we're doing is I'm trying to deal with the terms in this part of the equation. I'm taking, so we've got a pretty good feel for what's going on here. We did that, that was like the first thing we dealt with. Now it's inside an inverse, so we haven't quite dealt with that inverse yet, but we know the inside of the parenthesis. Now I'm trying to understand what's inside the summation. All right, well, I have a bunch of previous observations in there. What we're going to do, I'm going to take approximations of them using m data points of the white noise terms and leave those here. And so now what we're going to do is I replace this with the summation here and just slap it straight into the vector. And so then we get all of these. Now notice that we have w sub t, and then we have former observations of our white noise. Okay, so here, this is the white noise value that we are looking to get on the next observation. And then here, these all use past values of the white noise that we've looked at. All right, so now you'll notice that here, this is going to depend on a whole bunch of different white noise values all the way out to here. So if I go as far back as I can, this value is going to be in there. If I think about the first value I have here, that's going to be with a t minus 1. So here, all of these are going to appear inside this vector within the summations. And then I have w sub t right there. All right, so what this says is that this vector depends on m plus p plus 1 white noise values. All right, so now what we want to do is we want to look at this. We want to keep this in our minds. For the moment, let's take an arbitrary vector. Any vector. Think of any vector of length n. And what we're going to do is that we're going to take the dot product between this vector and this one. All right. And so now what we're going to end up doing is that I'm going to take the dot product between this vector and the arbitrary one, and I'm going to put it here. And then I'm going to do something that looks a little bit like an average. Looks maybe a little bit more than an average. It looks pretty close. All right. So now you'll notice I have a double indexed statistic right there. So this depends on sample size. This depends on how the size of the approximation that we have going on here. So here's the M. This is the number of white noise terms in the approximation, and N corresponds to the sample size that we've got at any given moment. All right, so now what we're going to do, we're going to say S of N is going to be equal to this. So here, this is all. So it's going to be equal to a similar, S of N is equal to a similar calculation, but you'll notice instead of approximating with white noise, we're actually using U sub T, which is equal to the backshift vector times the white noise process. So here we're using approximations for our X's inside here. Well, here we're actually using the actual X's inside here. But I'm using the same arbitrary vector both times, and I'm dividing by the square root of n both times. All right, so now we're going to apply a central limit theorem as n goes to infinity for a fixed number of terms in the summation up here. So in these summations here, when I take this limit, I'm going to say that I've got a fixed value of m, and I'm not changing that. That is a fixed constant value. All right, so my approximation for any given x uses m, fixed value, number of independent identically distributed white noise terms. And then we're going to say, hey, what happens as we let the sample size go to infinity, as I have infinitely many observations? All right, well, what's going to end up happening is that this is going to converge. All right, and what we're going to do is, we're just going to say y sub m is whatever it is that it converges to. All right, so, and what's going to happen is it's going to converge in distribution. All right, so, and the reason why I know this is going to happen is, it's similar to, convergence in, on the mean. It's not quite the mean, but it's pretty similar if you're not too strong on this aspect of theoretical statistics, that this is converging in distribution, similar to an average converging, a little bit different, but close. So here we know it converges to something. I'm going to say that this is that something. And so what we're going to do is that, remember that we have the X approximation here. So this approximates the time series that we want to know. So we have the time series we want, we have this, and then we're using that to converge to something here and here. All right, so we have y sub mn, which is converging to this. And so now, by construction, the distribution of what this converges to will be asymptotically normal with a covariance of the lambda times the covariance using the m term. So if I take the covariance matrix here, I know that that's going to be part of the asymptotic normal covariance matrix. Now, if I get a a larger and larger approximating, a larger summation for the approximation, I'm going to get a better approximation. And because of that, the approximating matrix is going to converge to the matrix that we actually we want to be working with as m goes to infinity. All right, so y sub m converges in distribution to a normal random variable with mean zero and variance of the vector that's arbitrary that we picked, conjugating the covariance matrix that we want to actually have in there. All right, so now this gets us to the second criteria. So we've met first and second criteria of the basic approximation theorem. Remember, I said there are 3 bridges, and we've made it through 3 of them. Let's make it to the last one. All right, so x sub t is a causal process by assumption. And so that means that I can write my time series values as an infinite sum on the white noise terms. Okay. And so it works out that if I subtract off that approximating value, so remember what the approximating value looks like. Here, the approximating value is a finite linear combination of white noise terms from the past. Here, I'm taking all the white noise terms up to infinity. Okay. So when I do that, if I subtract, well, what's going to happen? Well, those first finite, 0 through m terms in the summation are going to cancel out in this subtraction. When they cancel out, I'm left with everything m plus 1 and greater in index. Okay. Well, this, by saying that x sub t is causal, that tells me immediately, and this is from real analysis, from advanced calculus, that this summation converges, and for any arbitrary value, if I select a large enough little m, I know that the summation has to be less than the arbitrary cutoff that I'm interested in. So for any given epsilon, there exists an n such that if m is greater than n, then the summation will be less than epsilon. If you've taken advanced calculus, if you've taken real analysis, you know this off the top of your head. All right, so now we know that this, to get that convergence aspect, this has to be really, really small. And if I let m get bigger and bigger and bigger, what's going to happen is that this has to get smaller and smaller and smaller. And so that means that this has to go to 0 as m goes to infinity. And so now, if I think about u sub t minus u sub t exponent m, this is going to be the components of this difference. All right, so if I sit down and I work through this, if I think about this S sub n that we talked about a moment ago and that double index, what this tells me is that this has to be, when I square it, the expected value has to be getting small. And since it's getting small, I know that this whole thing has to shrink down to 0 for sufficiently large m. Now, something that's interesting is we didn't say what the lambda vector was. That's coming up. All right, so if I sit down and I just work through the ugly details of this expected value of a squared will be equal to this. And I know that these individual terms are going to be super close to 0 if I go with a large enough value of m. Or if it's close enough, if it's pretty close to 0, then everything is going to work out. And you notice I'm taking an average of super small values. Taking an average of super small values, I'm going to get a super small average overall. Boom, I'm going to have that this expected value squared converges to 0. All right, so that is the last bridge of the basic approximation theorem. All right, so this part here is saying that I can approximate the thing I'm interested in with a double indexed random variable. That double indexed random variable can be approximated with a single indexed random variable, which has in convergence the distribution of another random variable. What we're going to do, the one that we're interested in, is going to converge to the distribution of that last one. And we've just shown that. All right, so that tells us that S of n converges to the distribution of y, which we've already established is normal with this variance term. All right, so now let's rewrite what S sub n is just so that we know. Now what we're going to do, I'm going to replace this lambda vector with a constant 1 over the standard deviation of our white noise. Why did I choose it? Because the math works out. It's beautiful. It's beautiful. When I do that, here, so far in this proof, that lambda vector could have been anything. But now we're going to nail it down. Why we're going to nail it down this way? Because it works out. Okay, so here, S of n is going to be equal to this times all the other stuff, because this is now a constant vector. So I'm just going to go ahead and factor out that constant. Boom, we've got it. Now, what we're going to do is I'm going to take a look at this, and I realize, well, hey, that's u sub t. Huh. That's u sub t. And I've got the 1 over square root n here. I've got the 1 over square root n. This is u sub t. All right, so this is almost S sub n. It's almost, not quite. I've got the sigma floating around. Well, what I'm going to do, I go ahead and just multiply both sides of this by the sigma sub w. And what's going to end up happening is that this whole part is equal to capital S sub n times sigma. And this inverse part just stays the same. All right, so now I've worked out exactly what's going on. I know what this is going to converge to in distribution because I know how this will converge in distribution. This is a constant, because we're dealing with past values. That's a constant. And this is coming from that double indexed stuff. All right, so now I know that this part converges to gamma sub p. So that tells me about here. And so I could replace this here in the limits with gamma sub p. And it works out that for a matrix to converge in probability, then its inverse, if it exists, converges in probability also. All right, so what ends up happening when I go through and I apply all the aspects of the basic approximation theorem, that this thing right here converges in distribution to a normal random variable, mean zero. And here I've got that variance term where I'm just plugging in the right parts into what we talked about earlier. If I scroll up in the page, hit rewind. Now I notice, go, hey, whoa, 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 whoa. Those are inverses of each other. They cancel, become the identity matrix. Identity matrix is nothing in matrix multiplication. So that becomes exactly what we wanted. We have the distribution. Now there's one part left. One thing left. We're almost there. If we were being honest with ourselves, we haven't really addressed the variance correctly because we were working not with the estimated coefficients, the formula that we actually use. We change the index on that, and that changes the variance. But it's going to work out that everything's okay because, once again, what we have is going to converge to what we want. All right, so what's going to end up happening is that asymptotically, this is going to have the same limits as our estimated value of our white noise variance. All right, so for large sample size, this variance is going to be close to the variance we observe from our IID white noise values, and it's going to end up converging to what we want it to. Since both of them converge to the same thing, and this one is easier to work with, boom, we're going to have the result that we want. All right, so here I'm just going to go through and type this out, and it's literally just a plug and chug. It's super easy proof. It looks like a lot. It's not. All right, so here is just the definition. You'll notice that the index starts at 1 for this one instead of later on in the indices. And so now I'm just going to go through, replace this with what I need to have in that position. And now I'm just going to be just slugging through the aspects of this. All right, well, here we're just going to be working through it. Oh, so here I'm taking a transpose. So I have a parenthesis of transpose. Remember that the transpose of A times B transpose is equal to B transpose A transpose. So if I have two items multiplied, then transpose, it's the transpose of each one, but reverse the order. That's what we do here. All right, so now I'm going to go ahead and deal with this square. And you'll notice that this gets a lot wider, a lot bigger quickly. So here is, I square this part, it's here. This part gets squared, and that is all of this junk here. That corresponds to that squaring. You notice I haven't put any squares, I just put them next to each other explicitly. And then the cross multiplication term is here. And you'll notice I've got 2 go along with it. And it's a -2 because of the subtraction. So now I'm going to go through, I'm just going to start slugging through this. All right, well, this is a scalar. So I can move this around freely in matrix multiplication. So I go ahead and move it to here. And in all of this, I'm moving the constants any way I want to. I can do that freely. That's okay. And so I'm moving one of them back here. Now I am going to go ahead and take this, and I realize I am multiplying on the right by summation. I can distribute. Well, distribute will be the same as bringing it on the inside of this. If I bring it on the inside of this summation, I'll recognize that after I bring it on the inside of the summation, it's going to be the same as this, but without that inverse term. And so I know they're going to cancel out. And so boom, I'm going to have that. This x sub t appears here. If you go through bit by bit, you'll see that everything matches up perfectly. And so now I realize that this part here equals this part. And I've got a -2 in front of this, so then it becomes a -1. So now I'm looking at that, and so that's a pretty ugly thing. So here I've got 1 over n. I mean that I can always do a convergence on that, right? A convergence in probability, it's going to go to its expected value. All right, well that's nice. Here I don't have that. I have the summation, so it looks like a mean, but I don't have the 1 over n. But wait, let's pull a trick. What I'm going to do, I'm going to multiply and divide by n. Okay, so when I multiply and divide by n, that doesn't change anything. Multiplying and dividing by the same thing is the same as multiplying by 1. All right, so imagine I take a fraction, n over n. Doesn't change anything. I'm going to take the n on the bottom, and I'm going to go ahead and put it with one part over here. You'll notice it's going to end up in this position. Now, inside here, I'm going to have, I have an n, but I want to bring it on the inside, so it's going to be 1 over n. And now there's another step in this, and this is dealing with, so something I did not talk about is that I've still got a big summation to deal with over here. And I've got repeated indices. So there's another, so this summation is for the whole kit and caboodle over here. That summation is across the entire kit and caboodle. So I'm going to go ahead and I'm going to bring that across the entire summation. So here it's still on the, like on the outside. I could use an extra parenthesis. But I'm going to go ahead and distribute across here, and that's where this summation comes from. Is from adding up this term and adding up this term on the inside of the summation. The authors chose to like overlap on the indices just to keep it sane. So it's easier to keep track of it as you do the pencil and paper. It's not the clearest when you write, and try to interpret the proof. All right, so now when I do that, notice that there's a 1 over n. So now I have all these 1 over n's floating around, and I notice that, hey, I've got stuff that looks pretty good because I notice I've got this here. And I realize that this is going to converge to this. This is going to converge to that. This converges to the variance part. There should be a subtraction here. That subtraction should be right there. And this inverse converges to the inverse of the covariance matrix. And so I know that this is going to converge to the variance of our white noise process. I've got finally, this is a beautiful result. This is a beautiful proof. It's some tough sledding, but this is awesome. This is great. So this is saying that number one, when I have an autoregressive process, if I know the order, I can use the least squares estimate to get a good solid estimate as long as I have a sufficient data size. But wait, there's more. So it's going to have my estimated values are going to have the expected value I want. I know the variance aspect, and I know the distribution for large, approximately speaking. I know the distribution if I have a large sample size. And so not only so the first and foremost, when I make the approximation, this is saying the expected value is what it is supposed to be. This tells me the variance, and this tells me the distribution so that I can do hypothesis testing. All right, that's all I've got for you. Life is short, do math.